Welcome to my new calculus channel. I am John Gabriel. In this video I'm going to be talking about something known as Peano's axioms. As a matter of fact, I don't call them axioms, but I call them Crapaxioms, because they're not axioms of any kind, and they don't belong in mathematics, they don't belong in set theory, they just don't belong. The author of these axioms is this primate looking individual right here called Giuseppe Peano. Have you ever seen a more stupid looking moron than this? Okay, well, that's kind of nasty of me, but believe it or not, this individual here has greatly influenced mathematics, modern mathematics, with his set of 5 axioms. And I'm going to show you now how ridiculous are every one of these axioms. They don't make sense, they're completely irrational, and it's just unbelievable that something like this could take root in a field such as mathematics. It's simply beyond me. So let's start off with the first one. 0 is a number. Okay, so we begin the first axiom without even the definition of number. What is a number? We have no idea what is a number. The Greeks put a lot of effort, the ancient Greeks put a lot of effort into defining the concept of number. And if you look at what Euclid did, well, Euclid started off with ratios of magnitudes, right? So he said, well, compare AB to CD, where let's talk about magnitudes of length. But of course, you can apply this principle to any type of magnitude. Mass, area, it doesn't matter. But in this case here, let's talk of length. So if AB and CD are lengths, then the ratio AB to CD literally means AB compared with CD. Okay? That's what it means. That's how you read that. AB compared with CD. Now, in the beginning, there were no numbers. When Euclid started to derive the numbers, from the start, there was no such thing as number. So he had to compare magnitudes, the magnitudes AB and CD, whatever they were. Let's say AB was this line and CD was this line. Okay? So the comparison of these magnitudes, CD might be longer or shorter, it doesn't matter. Okay? Now, by comparing these two lines, Euclid was able to perform something called qualitative trichotomy. Okay? Trichotomy. That means he could if he could tell that the two lines were of different lengths, then he could say, well, that one was shorter or the other was longer. And thus he had performed measure. Okay? Qualitative trichotomy or qualitative measure was the first kind of measure. In other words, a measure without numbers. Right? So the next stage after this, which I'll discuss in a moment, will tell us the quantum leap that took place in order for the derivation of numbers. But notice here that in qualitative trichotomy, you can only say whether one length is greater or less than the other length, but not by how much, right? For example, if AB is shorter than CD, you can't say how much shorter AB is than CD, or how much longer CD is than AB. So it's not really the best kind of measurement, is it? And so Euclid decided, he had an idea, and the idea was to establish a standard magnitude, okay, a standard magnitude, which he would call a unit, and the unit would be just whatever ratio it was, let's say whatever magnitude compared to itself. So if you define a particular magnitude as a unit, then really what you're doing is this: you're saying that magnitude compared with itself, right? So that was the first ratio. So very good. Now, with the introduction of the unit, Euclid could now begin to define magnitudes that were multiples of the unit. So for example, if the unit was this length, then taking that length and placing it alongside another length produces another magnitude which is twice as long as that, right? Okay, so if this is the unit and this is a multiple of the unit, let's just call it 2. It doesn't really matter, but 2 is a multiple of the unit, and we would write this particular number as 2, which means 2 compared to 1, right? And eventually what happened was we dropped off this particular part here where it became understood that we were talking about units only. Okay, so this means 2 compared with 1. And much later we ended up with fractions. I'll get to that in a moment. But so now that Euclid was able to define these numbers, okay, etc., if the magnitudes were any of these, then after he compared them, say for example he compared 2 and 3, he'd be able to tell how much bigger than 2 is 3 or how much smaller than 2 is 3. So now he was able to perform quantitative measurement. Yes, that is measurement with numbers. Okay, you can also call this quantitative trichotomy. In other words, now Euclid could tell exactly whether 2 magnitudes were equal, okay, or less than or greater than each other. Alright, so this measurement now, it was a quantum leap over the previous qualitative trichotomy, all because of this blockbuster discovery, the unit. Okay? Alright, so now the next step in Euclid's derivation of number is that not all magnitudes are multiples of the unit, right? In other words, if this is a unit and we had some portion of the unit, let's say that much, then how would we represent that? Right? And so the problem arose where you'd end up no longer comparing ratios of magnitudes, but ratios of numbers. So the next step was ratios of numbers. So for example, if you said 1 to 3 now, like that, what it would mean is 1 compared with 3 units, right? So all these here are of the same length. Okay. So, and this here would give the idea, or is the idea of a fraction, like that. And similarly, 3, 1 is the idea of a fraction like that, right? So 3, 1 is this, and 1, 3 is this. So now we have fractions. And these fractions are also called rational numbers. Rational numbers. I'm going to stop here because there are no other numbers besides the rational numbers. There is no such thing as an irrational number, but that's not the topic of my video, so I'm not going to go into it right now. But if you'd like, you can read the complete derivation of numbers at this link here, which I will post in the comment section of my YouTube video. Okay, it describes everything about numbers and how we got them, and all the correct axioms, and gives you a lot of background into how we got number. So I'll post that link later so that you can read it if you wish. But Euclid was now able to complete the derivation of number from scratch. This is a perfect derivation. Okay, it's perfect. It doesn't matter whether Euclid thought of it or not, or any other mind thought of it or not. It would exist, it has existed in past perpetuity, it exists now, and it shall continue to exist even if there is no mind to think of it. It is a perfect concept, a perfect derivation. Alright, So now let's just leave that alone and go back to our discussion of Peano's Crapaxioms. So we saw that 0 is a number is completely meaningless because a lot of work went into defining number. As you saw on the previous slide or sheet that I was working, you can't just say something is a number without explaining what is a number. And of course, Peano never understood what is a number. In fact, after Euclid and before I came along, no one had a clue what is a magnitude or a number. That's a pretty big statement, but it's a fact, and I proved it. Okay, so modern professors of mathematics and teachers have no idea what is a number. In fact, some of the silly things they say is that natural numbers came first. Nothing could be more untrue than that. Ratios of magnitudes came first. In fact, all natural numbers are ratios of integers. Okay, all natural numbers are ratios of integers, positive integers. And there are so many problems with modern mathematics, but let's just stay focused here on Peano's Crapaxioms. So we've dealt with number 1. So already in the very first axiom we have a failure. Okay, so this is ill-formed, therefore it's a failure on Peano's part. So now in step 2 we see if A is a number, so we have a conditional now. If A is a number, well, what else can A be if we're dealing with numbers? One immediately begins to think. Then the successor of A is a number. Oops, the successor. So not only don't we know what is a number, but now we have a successor of a number. Just think about that for a moment. A number that comes after another number? Well, if you have rational numbers, then there is no number that comes after 0, is there? What is the rational number that comes after 0? What? Isn't that just junk? So not only can't you get to the construction of the real numbers, but you can't even get to the construction of the rational numbers. And there are so many morons in modern mathematics that subscribe to this absolute rot. Okay, step 3. We have 0 is not the successor of a number. Wow. Oh, so there is no number less than 0? There is no number less than 0? That's just simply amazing. In other words, no negative numbers, nothing else but 0 and what follows it. So we already have 3 failures. And then we get on to the 4th, which is kind of hilarious. The 4th one is really redundant, okay, because we don't know what is a successor. So it's telling us something about equality, but we don't know what is a successor. So we can't even begin to determine equality. Fine. And number 5 is an attempt to define infinity using set theory. But if you have studied set theory, you'll see that in Zermelo-Fraenkel or ZF set theory, this is called the axiom of infinity. And normally it's written down as follows. I hope I'll get it right. It's a bunch of rubbish, but anyway, it's something to the effect that there exists an X such that the empty set, okay, is an element of X or is in X, yes, and for all, actually I wouldn't say for all, there exists a set X such that the empty set is an element of X, and for all Y, now Y is not a set, it's just an element. For all Y is an element of X, the union of Y with its singleton is also an element of X. Okay, so it goes something like this. And what this here really means is that you have a pairing of y as follows, and so that means that really you're just looking at the element y and nothing else. Okay, so a singleton is usually what is meant by this notation here. So really what Peano was trying to do here is define infinity, and this later led to the axiom of infinity, which is also a bunch of rot, which is this here. Okay, total garbage. And so we can see that all 5 axioms are junk. Okay, they're all absolute rubbish, and yet these are the basis for the version of number theory known as Peano arithmetic, and these are taught as part of basic analysis or real analysis at university. You can't get a BSc in mathematics unless you pass an exam on this rot, which is quite incredible, because this baboon here, who was no mathematician of any kind, is the source of this rubbish. Okay, and I have nothing but contempt for this fool, because he didn't know any mathematics. Well, there's something else I'd like to add to this. In set theory, not there. Oh, before I go to that, you can find a valid proof that there is no such thing as an irrational number in this comment of mine on space-time and the universe. Okay, I actually proved that Dedekind cuts and Cauchy sequences are not valid constructions of real numbers, and you can read all about it here. All right, on this page. I will also provide a link to this comment in the comment section of the YouTube video. And now finally, after Peano, we got Gödel. This is really something else which is also quite incredible, because it's so mind-numbingly stupid that one wonders how it ever came to form a part of modern mathematics. But it's Gödel's incompleteness theorem, of which the representability theorem is one part. And so it says, in any consistent formal system which contains Q, okay, 1, a set is strongly representable if and only if it is recursive. You should ask yourself, what makes recursion special? Really, why is something strongly representable if and only if it is recursive? I've asked myself that question many times, and I've actually studied this Gödel incompleteness theorem. It's also a load of rubbish. And the other one is that it's weakly representable if and only if it's recursively enumerable. Okay, so really what it's saying here is that S is strongly representable in a formal system if and only if it is recursive. Okay, you can read up on this link here. It's available at Stanford's site, and if you just type Gödel completeness on the Google search bar or some other search engine, it should bring up this link here at some or other point. Okay, so a lot of rubbish arose from this moron's ideas here. I mean, Peano's axioms. Axiom is not even the right word to use. Peano's juvenile ideas is more appropriate for this rubbish. I can't even begin to express the amount of contempt I have for this fool, and for any fool who actually subscribes to his ideas. No one who subscribes to Peano Crapaxioms is worthy to be called an academic, never mind a mathematician. Well, I think that's pretty much all I wanted to cover in this edition, in this YouTube video, so I'm going to leave it at that. This is the New Calculus channel, and I'm John Gabriel. Till next time.